Okay, Cap BC, Unit 3, Day 2 assignment. I'm changing it to odds if you hadn't received that message. I think the odds be enough work. First problem state whether or not the function satisfies the hypothesis of the mean value theorem on the given interval. That being, does it meet the conditions if this is true? B, if it does, find each value of C on the interval A to B that satisfies the equation. So, does it meet the requirements for mean value theorem? Does it satisfy the hypothesis? And then if it does, what are the guaranteed spots where the actual slope, actual derivative equals the average derivative? So, number one function is f of x equals x squared plus 2x minus 1 on the interval 0 to 1. So, is it continuous on the closed interval? Yes, it is continuous. So, it is continuous on a closed interval 0 to 1. And then, is it differentiable? Yes. All polynomials are nice, smooth graphs. So it is differentiable on the open interval. So the answer for part A is yes, it meets the hypothesis of the mean value theorem. Okay, part B says to find the guaranteed value. So we would want to find the average slope first, f prime average, and that's going to be f1 minus f0, or 1 minus 0. Plug 1 in here, you get 2. Plug 0 in there, you get negative 1. So it's going to be 3 over 1 is 3. So that's your f prime average. And then we're going to take find f prime as a function and set it equal to the average. So C equals 1/2. It needs to be between the endpoints it is. And you better get an answer it does because it satisfies hypothesis. So that's what we're doing on these first ones. 3 function is x to the 1/3 on negative 1 to 1. So part A, is it continuous on the closed interval? Yes. Now, this graph, by the way, looks like it's like a cube. This is the inverse of a cubic. So it looks like a cubic flipped across y equals x. So it does look continuous on the closed interval. Is it differentiable? Now it looks, nice and smooth, but finding the derivative actually will help us sometimes decide if the derivative exists everywhere, because that's what differentiable, means. So this is powerful, and we would do this anyways if it did work. And we have a problem. When x equals 0, f prime of 0 is undefined. It actually is infinitely steep. So you get this like vertical tangent right there. So that's a problem in general. So it is continuous on the closed interval, but it is not differentiable on the open interval. So we can't technically use that. So we're going to say the answer is no for part A, which means we don't do part B. Okay. So that's number 3. Number 5 function is inverse sine -1 to 1. Now, I think a lot of times, thinking about what the graphs look like is helpful. That's one of the reasons that we made sure we're really good at all these graphs. So inverse sine is like the sine graph flipped across y equals x, and it ends up looking like that. And then we also have to just work with principal values. So this is inverse sine right here. Now, its domain actually is -1 to 1 because that's the range of the original trig graph, but everything x becomes y becomes x. So it is, it is continuous on -1 to 1, barely. It is differentiable. It isn't differentiable at the edges, one, because they're edges, but two, because it actually has a vertical tangent. But it doesn't need to be differentiable at the edges, just all the way up to it. So the answer is yes. We should be able to use mean value theorem. So now we got to find this. So we got to find f prime average, which equals f of 1 minus f of -1, or 1 minus -1. And f of 1's inverse sine of 1. Now it's this right here, gives you pi over 2, and then it goes down to negative pi over 2. So f of -1 is pi over 2, and f of positive 1 is pi over 2. F of -1 is negative pi over 2. And so then we get plus 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 plus. We get pi over 2 as the average slope. So then we're going to find the actual equation for the derivative. This one's a little tricky. I don't know if you guys remember the derivative inverse sine. It's 1 over the square root of 1 minus x squared. And we're going to set that equal to pi over 2. And then we're going to solve this. So we could flip both sides if that makes it easier. We could then square both sides. We could then subtract 1 from both sides for the least common denominator. And then there's still a negative there, so then we could divide a negative out of both sides. And then we could take the square root of both sides, plus or minus. Okay. And I think we expect to maybe get two answers here, just from a rough sketch. That would be the secant line. So here's one and here's one. So we kind of expect to get two of them. So hopefully you're doing that plus or minus. So the C value is plus or minus the square root of pi minus 4 over pi. Now this better be between -1 and 1. We could estimate it, or you could use a calculator. And I think it is 0.771. So that's good. If I wasn't using a calculator, I'd say, well, that's about 3 minus 4 is 1. Oh, that's negative. Let's see. Let's make sure I didn't make a mistake here. Oh, I did make a little mistake because that's pi squared. Because I was about to say this is going to give me a imaginary answer. So I'm glad I caught that. Okay. Now, pi squared, well, that's like 9 minus 4 is 5 over 9. It's about 5/9. So the square root of 5/9 is 0.771. So there you go. Number 7, same group of problems. So this is a piecewise function. And again, I think drawing a sketch of this graph is going to help you. understand what's going on better, especially piecewise functions. And this is supposed to be on 0 to pi. So I'm going to draw sketches. It should be easy. It's just a regular sine curve, cosine curve. So from 0 to pi over 2, so we'll go to pi over 2. And so the cosine curve starts at 1 and then goes down to 0 and then goes down to -1, right? That's the cosine curve. And we're really just looking at this part right here. Solid dot, open dot, that part. And then it's a sine curve, which starts here at 0, goes to 1, goes to 0, keeps going. So this is the sine curve. And we're using it from pi over 2, including solid dot, to pi. So that's that. So this is what this graph looks like. So in part A, we're trying to figure out, is it continuous on the closed interval? Not continuous on the closed interval. So you just say it right now. Done, doesn't meet the hypothesis of mean value theorem. But because it is not continuous, it is also not differentiable at pi over 2 specifically on the open interval. So the answer is no, we're not going to do mean value theorem. So we bail on it. Next set of problems, or the next problem, 9 says on the interval given let a equal f of a, b, write an equation for the secant line and then the tangent line of the function that's parallel to AB. So this is, we're trying to find, I did this a little bit in the notes. We want to find the equation of the secant line that's used to find the average slope. And then we also want to find the special places where the tangent line is parallel to the secant line. So the first thing we got to do is we got to make sure, well, can we use it from 0.5 to 2? This is not continuous at x equals 0. This is a vertical asymptote, but that's fine for us. I believe it should be differentiable from 0.5 to 2. When we find the derivative, that'll kind of help us figure that out more. But I believe it's continuous on the closed interval. And it is differentiable on the open interval, unless I find something else that contradicts that. Okay, so we got to find the average slope, f prime average. And so that's going to be f of 2 minus f of 0.5 over 2 minus 0.5. And so if you plug 2 in here, you get a 2.5, 5 halves. Plug half in here, you get half plus 1 divided by 2 becomes 2. So you get 5 halves that way also. So you get 0 over 1.5 is 0. Now this is the slope of your secant line and your tangent line. So it's 0. But we got to find the special place where, and at this point, we could find the equation of the secant line, because it would be y minus 5 halves equals 0 times x minus 2. And that would be good enough. Or you could write in slope-intercept form, it'd be y equals 5 halves. It's a horizontal line. Or we could use the other point, y minus 5 halves equals 0 times x minus 0.5. Write that as your equation of your secant line. Or you could then change that to slope-intercept form, which would just, it's a horizontal line. So a couple options there. Now we got to find the equations of the tangent lines where that special guarantee of mean value theorem happens. So we got to find the actual derivative of the function, which is this. And by the way, this is undefined at x equals 0. F prime of 0 is undefined, so it's not differentiable at x equals 0. That's fine. That does not lie on the interval we're looking at, so that confirms it was differentiable. So we then are going to set this equal to the average slope and then solve for it. So 1 over x squared equals 1, x squared equals 1, square root of both sides, plus or minus. I need to see that plus or minus. So the C value, though, has to lie between 0.5 and 2. So the C value is 1. Then we need to plug this into the original function to find out what the y coordinate is at that point. And so it ends up being 2. So the equation of our tangent line is going to be y minus 2 equals 0 times x minus 1. And you could write that as the equation of your tangent line, or you could change it to slope-intercept form. It's a horizontal line. So there you go. 11 says a trucker handed in a ticket at a toll booth showing that in 2 hours she covered 159 miles on a toll road with a speed limit of 65 miles per hour. The trucker was cited for speeding. Why? Well, I guess we're assuming that law enforcement understands calculus, and so they found her average speed, which is a derivative, would be just the slope between the endpoints, 159 miles over 2 hours, which gives you 79.5 miles per hour. So by mean value theorem, and we're assuming that people drive continuously and differentiably. You can't just jump from one spot to another. You can't just, and you can't just change from one speed to another without going to the other speeds. So should meet the conditions at least once. The actual speed equals the average speed. And that was 79.5 miles per hour, which is greater than 65 miles per hour. So something like that. That's 11. And 13. Classical accounts tell us that our 170 or trireme, ancient Greek warship, once covered 184 sea miles in 24 hours. Explain why at some point during this feat, the speed exceeded 7.5 knots, which is sea miles per hour. Okay, well, I guess we should figure out how many sea miles per hour were covered. So this is your average speed derivative, rise over one run. So let's see, that's going to be 92 over 12. It's going to be 46 over 6. That's going to be 23 over 3, which is 7 2/3 sea miles per hour, which is what knots are. So that's the average. So by mean value theorem, at least once the actual speed equals the average speed, which was 7 2/3 knots, which is greater than 7.5 knots. So there you go. That's it.